Last class we started with the switched capacitor circuit and we discussed about switched capacitor resistor and switched capacitor low pass filter. So in switched capacitor resistor, a resistor can be implemented using a capacitor and two switches. The switches are controlled by non-overlapping clock signals, okay, phi 1 and phi 2, and the condition is that on time of both the clock signal is less than total time by t by 2, okay, and the t of both the signal must be same, and it must be actually it is complement to each other, and the on time is somewhat less than that of the off time. And here we discussed a simple sample and hold circuit. Actually it is not in our syllabus, and here we derive the parallel switched capacitor equivalent circuit, and we discussed the switched capacitor filter also. In filter we drawn a normal filter circuit RC filter, and that R is replaced with a capacitor. We created an equivalent R from that capacitor using clock signals, and the value of R is T by C1. This one is already we proved in resistor implementation. And next we try to find the transfer function of this one. So we are trying to proving that this one will act as a low pass filter. For that we derive the transfer function of this one, and deriving the transfer function we considered a full clock cycle, full clock cycle signal, and we find the value of V2 of t or Vn of t in terms of input signal as a function of V1 of n minus t, okay, and then we derive the transfer function. For deriving that we consider the two clock cycle n minus 1 one clock cycle, that is n minus 1t to nt. In first half of the clock cycle phi 1 C1 will charge, and in next half cycle phi 2 C1 will discharge to C2. And the idea or the derivation, when we phi 1 is active, C1 charges from input, and it is equal to V1 of n minus 1t. C2 will hold its previous charge. This C2 will hold its previous charge. So the voltage across C2 is V2, the previous charge, we output to n minus 3 by 2 of t. Okay, because the voltage across C2 changes only at n minus 3 by 2, n minus 1 by 2, n plus 1 by 2, etc. The odd half of the cycle. And this will be an equivalent circuit of this same circuit. Here the capacitor is splitted into a normal capacitor, uncharged capacitor, and a supply voltage. And during the next half cycle, phi 2 is on, phi 1 is off. So this capacitor is isolated from input. C1 discharges to C2. So C2 already have some voltage. So the charge in C2 and C1 are redistributed. Charge in C2 and C1 are redistributed, and the output voltage V2 of n minus 1 by 2 t we can calculate using superposition theorem. It's become C1 by this value, C1 by C1 plus C2 into V1 of n minus 1t, and C2 by C1 plus C2 into V2 of, this is the previous charge in the output capacitor, okay, and that same value V2 of n minus 1 by 2 is kept in the capacitor itself for the next half cycle also, so which is equal to V2 of n minus 1 into t here. So from this one we derive the transfer function, and we proved that the transfer function is equivalent to a transfer function of low pass filter. So the circuit will act as a low pass filter. So in this section we are going to implement switched capacitor integrator. Okay, switched capacitor integrator. Here also we are starting with the normal analog integrator using op-amp. Okay, because the earlier circuit itself will act as an integrator. The low pass filter is another form of integrator under some conditions. So this one will also act as a integrator. That also will act as integrator, and This one will also act as integrator. This is a active uh, integrator because it consists of an amplifier. So in this circuit, if R1 is replaced with the switched capacitor, it will become a switched capacitor integrator. So here we can replace that capacitor using, or that resistor using a capacitor C1 and two switches S1 and S2 with the control signal phi 1 and phi 2. Phi 1 and phi 2 are non-overlapping. Overlapping, and time period T1 of phi 1 and phi 2 is less than T by 2. Less than, or it's less than approximately equal to T by 2. Okay. But we are not deriving the transfer function of this one, but we need to derive the transfer function of another switched capacitor integrator. This circuit is not used in practical applications because it have a parasitic capacitance effect. The drawback is parasitic capacitance effect. So due to that, this circuit is normally not used in practical integrator implementation because the output may vary due to the parasitic capacitor present at this point. The reason of this one, during the charging, when phi 1 is on, the capacitor C1 is charged via this one. Okay, capacitor is charged via this one, and due to, assume there is a parasitic capacitance at a point P. Assume there is a parasitic capacitance at a point P. That also may charge due to this Vin. Okay, parasitic means due to the capacitance between two connecting wires or due to some other depletion capacitance or something like that. Okay, so due to the parasitic capacitance, that may also charge from the Vin. Okay, if we take the same path to discharge C2 through the P itself, the parasitic point P itself, if we discharge to C2, what happened? These two effective capacitance or two effective charges will discharge to C2 and output may differ. Okay, output may differ. So to solve this problem, to overcome this problem, we need to implement a circuit. The charging path is entirely different from the discharging path, or the parasitic points, the charging point is connected to ground, or we will take the discharge path from the ground terminal of the capacitor. So if we take a discharge path from this point of the capacitor, what happened? During charging path, that terminals are grounded, so it will not charge from the supply. Even if some capacitance is here, it cannot charge due to input signal. So if we take a discharge path from here, or the second terminal of capacitor, okay, if we take a discharge path from the second terminal of capacitor, which is already grounded, during the charging time, we can eliminate that parasitic capacitance effect. Okay, so we modify this one. We will modify this circuit. We modify this circuit like this, using two signal phi 1 and phi 2. The charging is like this, and we will discharge the capacitor like this. So in this case, this will be a common point in the discharging path. So what happened? Here it will be grounded. If there is some capacitor here, parasitic capacitance here, it will be discharged like this. And if there is a parasitic effect from these points, these elements, it is already grounded during the charging time. So there is no charge in that capacitor, parasitic capacitor, that present in this terminal of capacitor. So that will be not, that capacitor have no effect in this type of circuit. And if some parasitic okay, just a minute. If some parasitic capacitance are present here, assume some parasitic capacitance are present here, due to this discharge path, due to this phi 2, that capacitor will discharge through this one. There is no effect from this parasitic capacitor also. So effectively, during charging, these portions are connected to ground from the capacitor C1, and discharging time, these terminals are connected to ground. There is no parasitic capacitance effect in this implementation. Okay, that's advantage of this implementation. Both the terminal of the capacitor are grounded at least to one of the half cycle. Either phi 1 is on, either at the phi 2 is on. This circuit we can modify in another way or redraw. This just redraw in another way using this one. So this is the actual practical integrator circuit, op-amp integrator circuit, or switched capacitor, switched capacitor integrator. Okay, so here also we need to verify it is an integrator or not, and we need to derive the transfer function of this integrator. So this integrator there is no parasitic capacitance, and there is no, this parasitic capacitor is not there also, though there is no stray element. Okay, there is no 1 second, no wait a minute, stray means stray effect. Okay, stray effect. Okay, stray effect. And we will analyze this circuit and we will derive the transfer function of this circuit, and that derivation is same as that of the derivation that we used in low pass filter. Okay, the derivation is same as that of low pass filter, except there is a op-amp is there. As per the op-amp, there is no meaning because op-amp just will act as a active element to boost the or improve the impedance characteristics of the circuit. Okay, so deriving the transfer function of this circuit, here also we are considering phi 1 and phi 2 are non-overlapping. Phi 1 and phi 2 are non-overlapping, and during the phi 1, first we will analyze phi 1. During phi 1, the capacitor will charge. When phi 1 is on, the capacitor charge like this. When phi 2 is on, capacitor will discharge like this. Okay, that's all. Capacitor C1 will charge and capacitor C1 will discharge during phi 2. During phi 1, capacitor C1 charge. During phi 2, capacitor C1 discharge to C2. We need to find the output voltage. Okay, we need to find the output voltage. For analyzing this also, we are considering each half cycles. So initially, when phi 1 is, initial case phi 1 is on, when phi 1 is on, this capacitor, the charging capacitor, is not connected to op-amp. So the circuit looks like there is a C1 capacitor isolated and C2 capacitor is isolated. As due to the feedback, capacitor will hold the charge. That's all. Due to this feedback, capacitor cannot discharge and it will hold the charge. At beginning of at phi 1 is on, at t equal to n minus 1 t to n minus 1 by 2 t, because only half the cycle, half of the time period we are considered. That time C1 is charging, C2 hold its charge. Okay, C2 hold its charge. When phi 2 is on, C1 have some charge, that charge will be discharges to C2. Okay, when phi 1 is on, t equal to n minus 1 t to n minus 1 by 2 t, C1 charges, voltage across C1 become V in of n minus 1 t, fine, and V2 remain in the previous value equal to V2 of V out of n minus 1 t. There is no change to in n minus 1 by 2 t. Okay, during the phase phi 2, t equal to n minus 1 by 2 t to n minus 1, oh sorry, here it is to nt, and the C1 supply its charge to C2 and equilibrium condition will achieve and the output voltage will change. Okay, output voltage will change and we need to find the equation of that output voltage. During the second half cycle, circuit look like this. So C1 have some voltage V in of n minus 1 t. Here the capacitor have no charge because here the capacitor charge is separated as a voltage source, and C2 itself have an initial charge of sorry, uh, arise, arise. So C2 itself have some charge, and the charge is here, that is V out of n minus 1t, and these two together will produce another output voltage, and the output voltage is V out at n minus 1t by 2 when phi 2 is on, when the phi 2 is on, and that output will hold up to V out of n minus 1t also. Okay, that will be hold up to this one. So V out of n minus 1 by 2t equal to C1 by C2 V in n minus 1t, this supply voltage. As per the op-amp characteristics, these two terminals are virtually shorted. So we need to find voltage, output voltage from this to this ground. It consists of an output voltage V out equal to n minus 1t, and due to this supply voltage, this capacitor will charge. Okay, how much it will charge? It will distribute the charge between VC1 and C2. The output voltage will be distributed such a way that it is C1 by C2 into V in n minus 1t. Okay, this capacitor, this voltage will be there. This input voltage is distributed to C1 and C2, and from C1 it is to go to C2, and the ratio is C1 by C2 into V in of n minus 1t plus V out of n minus 1t. So from this one, V out is n minus 1t, this is also same. So from this one we can relate V out and V in. So deriving of transfer function, we will apply Z transform in this equation, and V out of Z is like C1 by C2 into Z inverse V in of Z inverse V out of Z, and the equation is looks like same as that of our low pass filter, or it is actually integrator. Okay, that's all. This transfer function is enough. And in textbook, they try to derive the relation between actual integrator and the integrator defined by this switched capacitor. In actual integrator, I think I missed that one. Actual integrator, here it is, right? Just a minute. For actual integrator, we know its low pass filter response h of e raised to j omega is 1 by j omega, or 1 by 1 plus j omega RC2, or it is approximated to 1 by j omega R1 C2. So we will try to develop a transfer function similar to this one. They try to develop a transfer function similar to this one from our h of z. To convert that into analog domain, we will substitute z equal to e raised to j omega t, and we will get it is h e raised to j omega t, e of j omega t, c1 by c2, and we will substitute z equal to e raised to j omega t and multiply and divide with e raised to minus j omega t. We will get an expression like this, and we will apply a condition to convert this equation. Similar to this one, we will apply an equation as omega t is small, this quantity will become 0, and these two quantity will become approaches 0, and it's approaches unity. It's not approaches 0, it's approaches unity. By differentiating that one, we can prove that it is approaches unity, and you will get a h of e raised to j omega t become c1 by j omega t c2. From that you will get r1 equal to t by c1, and integrator frequency omega equal to 1 by r1 c which is equal to R1 by Tc2. Actually this one is not required, as they derived in textbook, just explained. Okay, that's all. Next one, actually here one more thing we need to note, that the output voltage V0 by Vz, there is a negative time, there is no negative time, no negative. So this means it is a non-inverting integrator, non-inverting integrator. Okay, just note that one. Okay, so we actually derivation is started from a inverter integrator. Here it is negative, is supply is given to negative, so in inverting integrator. But in this configuration, stray insensitive integrator, we are getting a non-inverting integrator from this circuit. Okay, but if we change the uh, control signal, then we will get a inverting integrator. Okay, that circuit is explained here. If we change the control signal phi 1 to phi 2, and here it is phi 1 and here it is phi 1, discharging is take place like this, charging is like this control signal order is very important. Then only it will work as a integrator, or it will work as a switched capacitor resistor, So please note this order: phi 2 phi 1, here it is phi 2 phi 1. Earlier case is phi 1 phi 2, and here it is phi 1 and here it is phi 2 in the previous circuit. Only here the interchange take place. Then the output here will be inverting integrator. The output will be a negative of that input. Okay, so here also deriving the transfer function of this circuit, or evaluating the transfer function of this circuit, we will follow the same concept. We are considering a clock signal, and even and odd halves. Okay, each halves, and during considering the clock period from t equal to n minus 1 t to n minus 1 by 2 t, phi 1 is on. Assuming phi 1 is on, then capacitor will connected like this, right? Phi 1 is on. Wait a minute. This phi 1 is on. C1 charges and C2 hold its charge. I think I have phi 2. Have a doubt. Okay, sorry, my mistake. Written is correct. When phi 1 is on, C1 discharges via S2 and S3, and C2 hold its charge. Okay, when phi 1 is on, these two are connected together, and capacitor discharges via these 2 points. While discharging, all these elements are connected to ground, there is no stray capacitance. And while charging, here I am deleting all, when phi 2 is on, what happened? Phi 2 is on, the capacitor C1 is charges from V in, and the same will be supplied to capacitor C2. So during phi 1, we get phi 1 is on, Vc1 of capacitor is 0, Vc2 of n minus 1d is same as that of the previous half cycle, not full cycle, half cycle. V out of n minus 1 minus 1 by 2, or n minus 3 by 2 t. Okay, and during the phi 2 is on, from t to t equal to n minus 1 by 2 t to nt, capacitor C1 charges from V in via S1 and S4, like these two, S1 and S4. And the output voltage of capacitor Vc of n minus 1 by 2 t equal to V in of n minus 1 by 2 t. And output is remaining in that point itself, assume at the beginning. And what happened during the next? The capacitor will charge from this one. Okay, then the capacitor will Now this is the condition we have. After that, the C2 will charge from this one, or the output voltage will change. In that half cycle itself, the Vout at n minus 1 by 2 t or up to n minus 1 of t, the output voltage is nothing but the voltage across the capacitor C2 itself, V out of n minus 3 by 2 t, and it's plus this voltage. Okay, this voltage due to voltage in the capacitor C1. So the output voltage here, I think I missed this one, it's plus C1 by C2 again into V in of n minus 1 by 2 t. All the times are n minus 1 by 2, n minus 3 by 2 and n minus 1 by 2. So from here itself we can take the Z transform easily, and when we divide, oh, oh, there is a problem. Okay, I forgot one thing. I am from my mistake. Arise. This one is negative because during charging of this one, we are connecting plus minus, we are connecting this minus to the supply voltage, right? So the effective voltage in previous case, I think in just I want to clarify why the polarity is V0 here. The discharging path is like this itself. Oh, have a doubt. Just want to clarify that one. Why it is negative. Why this one is some want to supply the charge, right? Anyway, I will clarify that one. In this case, we are getting a negative voltage here. Okay, negative voltage, and then we can find the transfer function directly from this equation itself, and we will get h of z is equal to v out of z by v in of z, which is similar to the previous case, z by z minus 1, or C1 minus C1 by C2, 1 minus Z inverse you will get, and which is equivalent to an integrator. Okay, this session I will clarify in class itself. Okay, thank you.